All right, it's 11, so let's go ahead and begin. Today we are going to talk about filter circuits, and we're going to restrict things to passive first order filters today. So anybody have any idea what filter circuits might be used for? Let's start there. Anybody heard of filters or anything like that? Yes, sir. Pardon? Getting rid of distortion? Yes and no. And so what I mean by that is a filter is something that's used to get rid of a certain frequency or range of frequencies. So if distortion is occurring over those frequencies, then yes, you're correct. So for example, in electronic devices that are susceptible to 60 cycle hum, which is effectively noise due to poor grounding, and things like that in buildings, you might put a high pass filter in so that all of those 60 hertz oscillations get filtered out, and the only thing that gets sent to the output is the higher frequency terms. So to reiterate, filters are used to pass specific frequencies and attenuate others. And the ability of a circuit to perform this is based almost entirely on its impedance, which is something that we'll revisit or visit shortly. But before we get to that, I want to define some simple kind of building block filters as to how we're going to look at things. So let's start with a simple low pass filter. And we're going to consider an ideal case, which we literally cannot build, but it's just going to be informative to what we should expect our behavior to be. And we're also going to be dealing with the constraint that we have a passive filter, meaning that our output signal can never be larger than our input signal. All right, so with that in mind, the frequency response of a low pass filter should look something like this. This is our magnitude on the top axis, and this is frequency on the x-axis. And I'm trying to think of what I want to use. Let's just say, for the sake of argument, we're dealing with a voltage signal. Okay. So for a low pass filter, we would see that our output signal remains at its maximum until we reach a certain frequency called the cutoff frequency, which I'm going to denote as omega C, after which point 100% of the signal is attenuated. So for a low pass filter, everything to the left of omega C, or all signals have a frequency less than omega C, get passed. So we call this region the pass band. And everything to the right of omega C is attenuated or rejected. So we call this guy the reject or stop band. Now let's consider, let's just say, change my mind slightly on how I'm labeling that axis. It's going to be the ratio of V out to V in, which would be the magnitude of the transfer function. All right, so now let's say that we're dealing with an ideal high-pass filter. Here's omega. Here's the ratio of the output voltage to the input voltage. So for an ideal high-pass filter, we should observe that all of our signal is attenuated until we reach our corner frequency, omega c, at which point abruptly all frequencies of interest are passed. So every frequency below omega c constitutes our stop band, and everything above omega c is our pass band. So these are what we can make with simple first order circuits, meaning just resistors and capacitors or inductors. Our second order filters are our, let's say, band pass filter. We'll look at an ideal one of these guys. And a band stop filter. Also called a notch. Actually, I'm going to give myself a little bit more room here. All right, so for a band pass filter, we are going to have three specific frequencies of interest. I'm going to call the first one omega low. Then I'm going to have omega naught. And then I'm going to have omega high. And so in a band pass filter, we observe that all frequencies below omega low get rejected, and all frequencies above omega high get rejected. So we have a pass band that is centered on that middle frequency, omega naught. We have a stop band on either side of our pass band. For a band stop filter, we have those same frequencies of interest, omega low, omega naught, and omega high, but we have the exact opposite response, meaning we have two distinct pass bands. Everything below omega naught gets, or excuse me, omega low gets passed, and everything above omega high gets passed, and we have a notch in the middle that is centered around that intermediate frequency, omega naught. So these are our four basic types of filters. There are several other types of filters. So for example, in Circuits 3, you'll be introduced to Chevy-Chev filters and Butterworth filters and all that kind of good stuff. Those are just specialized architectures of creating low pass, high pass, band pass, or band stop filters. These are the four basic hierarchies of whether, defining which portion of the frequency spectrum will be accepted and which portion of the frequency spectrum will be rejected. And then we go on to specific circuits meant to perform these operations in different ways. So we are going to start our analysis with passive first order filter circuits. And generically speaking, I want to talk briefly about what we're going to be dealing with here, okay? So we are going to have some input signal that we'll consider to be 1∠0 volts. And this voltage signal, or this phasor, actually represents all frequencies. So it would be one cosine omega t, one cosine 2 omega t, one cosine 78.4 omega t, et cetera, et cetera. All of those input signals are represented by this simple phasor, right? So it's representative of all frequencies, starting from 0 radians per second all the way up to infinity radians per second. And we are going to connect our source to our filter circuit. Where this will for sure be a linear filter circuit because this is a low-level class. And what's happening is that this filter circuit is acting on our input. So we're going to give the name of the transfer, we're going to define the way that this circuit acts on our input signal as H. And it is what's going to be called the transfer function of our circuit. I'm trying to remember if in the homework assignment I call it H or G. Some books call it H, some books call it G. If I call it G in the homework assignment, I'll just go through and switch that. It won't be a big deal. And then we're going to measure some output phasor voltage. H of omega, and it's going to be a complex number, is simply going to be the ratio of the phasor output voltage divided by the phasor input voltage. And that's specifically why we're using 1∠0 volts as our input voltage, so that if we can determine what the output voltage of our system is and divide it by 1, we know the transfer function very, very easily. Because our transfer function is a complex number inherently, it will have some magnitude and it will also have a phase angle. And we're going to need to pay attention to both of those. So we call the magnitude of our transfer function the frequency response, and we call the phase angle of our transfer function the phase response. And they're both going to vary with frequency. Okay, so I want to be clear about that. All right, so with that in mind, let's take a look at a simple circuit. All right. So that was just kind of setting up things. So let's say that I have the following circuit. All right. How could we determine the transfer function for this guy? So I'm arguing that if I apply a time domain input signal and measure a time domain output signal, I could figure out what's going on with this guy, okay? So we are going to use steady state sinusoidal circuit analysis to figure out what our transfer function is. And it's literally just going to be a function of the impedance of this system. The reason why we can do this is a little bit beyond the scope of this class, but how many of you guys have had any experience in your math classes with a Fourier transform? So using Fourier transform techniques, we can convert any analog signal into the sum of potentially an infinite number of sinusoidal signals, all with different frequencies, right? And so we can see from that perspective, if we can make any time domain signal look like a whole bunch of sinusoids, we can see which portions of this signal are going to get rejected and which portions are going to get passed. So let's look at this thing in the frequency domain, which will be fairly trivial to convert over. Have our phasor input voltage. The impedance of our resistor remains the same. Close menu. We're going to be looking at the impedance of our capacitor, which will just be 1 over j omega c. And then here is our output signal. So, do we have the ability to construct a simple relationship for V out as a function of V in for this frequency domain circuit? How would we go about doing it, those of you nodding your heads? Too much work. Try again. Voltage division. This is a voltage divider circuit, 2 impedances in series, and we want to take the output signal over one of those impedances. That is correct. All right. So V out is simply going to be, hold on just one second. This has happened before. I need to reopen. Okay. Sorry, that little thing was just going to keep popping up over and over again and frustrating me. All right, so using voltage division, we'll have V out is equal to V in multiplied by 1 over j omega c divided by R plus j omega c, right? Just good old voltage division, nothing fancy there. So from this, we can say that our transfer function, h as a function of omega, sorry, this should be 1 over j omega c there, is 1 over j omega c divided by R plus 1 over j omega c. I typically prefer to not have fractions like that. So what I would do is multiply by j omega c over j omega c to clear my fractions. And this would give me 1 over 1 plus j omega RC. I've done my math correctly, which I believe I have. So this is our transfer function for this particular filter. If we wanted to know the frequency response specifically, we would need to take the magnitude of this guy, which we can do pretty easily, and I'll walk us through it momentarily. Looking at a plot of the magnitude of our transfer function as a function of omega will tell us exactly what type of filter this is. And we can also develop a phase response. So let's start by determining our frequency response, the magnitude of h of omega. Let me put this. So how might I go about determining the magnitude of this guy in a relatively straightforward fashion? Any thoughts? Can we all agree that the transfer function is a complex number? Let's start there. I have a, you could argue polar form or rectangular form complex number in the numerator, and I have a definitely rectangular form complex number in the denominator. My ultimate goal is to develop a relationship that tells me a couple of different things, right? I want the magnitude and I want to know the phase angle. So as a quick aside, the magnitude, let's say that we have a complex number A. In rectangular form, let's call it lowercase a plus jb. Dang it. Sorry, having a brain fart here. Erase that. The magnitude of complex number A is simply the square root of the real portion of A squared plus the imaginary portion of complex number A squared, and then we take the square root, which is from Pythagorean theorem. And the phase angle is given by the arctangent of the imaginary portion divided by the real portion. So let's call this I am A over real A. So I can determine my frequency response and my phase response by expressing h of omega as a rectangular form complex number. Can we agree with that sentiment, right? So if I can figure out what the real part is and I can figure out what the imaginary part is, I can throw them into these two equations and I will immediately get my frequency response and my phase response. So how can I convert my transfer function here, h of omega, into a rectangular form complex number with a discrete real part and a discrete imaginary part? Effectively, how do I get rid of the complex portion of the denominator there, which is what's screwing everything up for me being able to just directly apply these definitions? So I multiply by the complex conjugate and then divide by the complex conjugate as well, because I need to multiply by a factor of 1. All right, so in this case, we would have 1 plus j omega RC, our original function. And then I would have 1 minus j omega RC down here. Sorry, and 1 minus j omega RC here. And so what this is going to give me, 1 times 1. So let's see, for my denominator, this is going to look like 1 minus j squared, which is positive, omega RC, quantity squared. And then I will have 1 times 1 is 1, and 1 times minus j omega RC. So this is going to be I can't wait till my new pen comes in on tomorrow. Omega RC squared 1 plus all right. Anybody have any problems with this representation? All right, so from this, our frequency response is the square root of the real part squared plus the imaginary part squared. So I'm going to have omega RC squared, this whole quantity squared. Oops, I'm sorry. The imaginary part should not include the j. It should just have negative omega RC. So that will be omega RC quantity squared. Which gives me 1 plus omega RC quantity squared divided by 1 plus omega RC quantity squared squared. This guy cancels this guy, and I'm left with 1 over the square root of 1 plus omega RC quantity squared. So this is what my my frequency response is. Okay? The magnitude of my transfer function. So how can we determine what type of filter this is? Well, when omega is equal to 0, what value will our frequency response have? 1, right? Because we'll have 1 over the square root of 1, which is just 1. So for low frequencies, extremely low frequencies, all of our signal, input signal, gets transferred to the output. What about for very high frequencies? It's going to be 0, right? Because when omega approaches infinity, we're going to have 1 over infinity, which is 0. So we are passing very high frequencies and rejecting very low frequencies. What type of filter is this? A low pass filter. Absolutely right. That's how we test, right? For band stop and band pass filters, we would see that, so for band pass, we would see that at very low frequencies, the output is 0, and very high frequencies, the output is 0. For a band stop, very low frequencies, the output is 1, very high frequencies, the output is 1. And for a high pass filter, low frequencies give us 0, high frequencies give us 1. So it's really easy to see what type of filter circuit we have. All right, for our phase response. Theta as a function of omega, if you recall, is the arctangent of the imaginary portion, which in this case is negative omega RC divided by 1 plus omega RC quantity squared. All of this over the real portion, 1 over 1 plus omega RC squared. We have a common denominator for both fractions, so that cancels each other out. And so we are going to have negative arctangent of positive omega RC, or arctangent of negative omega RC. They're the exact same point. So we now know how the excuse me, how the filter circuit operates. So let's take a quick moment and simulate a circuit in LT Spice. I want to show you what these are going to look like. Let me get my mouse out. The schematic. Let's move this out of the way. All right, so let's see. I had a resistor. And I had a capacitor. That's where my ground is going to go. See if I have my other ones. I really care. And I need a voltage source. Wire. All right, so Let's pick a value for a resistor real quick. Just somebody throw something out. 1 kilo, all right. And pick a value for the capacitance, please. 1 microfarad, all right. To do this type of simulation, this is what's called an AC simulation, I believe, in LT Spice. We're going to go to advanced. And over here, where it says small signal AC analysis, that's what we're going to be dealing with, right? So we're going to leave all those functions to the left alone. We're not going to put in a DC value. We're simply going to put in an AC amplitude. I prefer 1, and then leave everything else alone because we're starting with a phase of 0. That'll work. And simulate. It's going to see. So we are going to be doing the AC analysis. So we can choose whether we're doing an octave, decade, linear. We're going to go decades, number of points per decade. Let's do something pretty large here. So let's say 1,000. Our start frequency, let's do it 1 millihertz. And our stop frequency, we'll do it all the way up to 1 megahertz. Probably, well, we'll see what happens. We can always adjust it. So we're starting at 1,000th of a hertz and ending at 1 million hertz. Let's see what happens just based on these numbers. All right, so if I click this node right here, this is effectively giving me my transfer function because I'm using an AC signal of 1 volt. All right. If you will notice, there are 2 waveforms. Can you guys see this green color, or do I need to change it? All right, let me go into settings real quick here. All right. So that blue is probably a little easier to see. All right. So there's a solid line and there is a dashed line. The solid line represents the transfer function or the magnitude of the frequency response. And the dashed line is the phase angle or the phase response, okay? So LT Spice automatically gives you both. However, I want to point out that it is not giving it not giving us the information in a way that we would be particularly used to seeing. And what I mean by that is look at the y-axis on the left-hand side of the screen. We are given our response in units of decibels, okay? This is what's commonly referred to as a Bode plot, okay? So we have units of decibels on our y-axis, and then we have a logarithmic plot as our x-axis. So we're not looking at things linearly, we're looking at it logarithmically here in this axis, okay? So LT Spice can't really back out to do a simple magnitude plot like MathCAD can. So I think when we have class on Wednesday, I'll show you how to use MathCAD to do these plots and generate Bode plots specifically so that you can compare your analytical work to the simulation to make sure that they're doing the same thing, that you're solving the circuits in the same way. But let's talk about something specific here, okay? So we can see that this is a low pass filter circuit because for all of our low frequencies, our output is 0 decibels, which corresponds exactly to 1. Our output versus input signal ratio of 1 to 1. at a specific frequency, we see that it starts to decay, but it's decaying very gradually in comparison to our brick wall ideal plot, okay? So this is one of the trade-offs of making an actual filter versus the ideal case, is we cannot have it fall very, very rapidly. Now we'll in your later EE classes, we will develop schemes by which the cutoff will occur over a much shorter frequency scale. But what that's going to do is it's going to mess with the amplitude while it's passing the signal. So we'll get some weird looking oscillations and stuff before it just straight falls down. And that's pretty typical of a Chebyshev filter. Butterworth filters look largely like this, and the cutoff gets steeper and steeper and steeper the more elements you put in to the system. So this would be considered like a first order Butterworth system, which is just a basic low pass filter. I want to define a particular frequency of interest for real filters. And that is what's called the negative 3 dB frequency, or the half power frequency. That is what we're going to consider our cutoff frequency for this particular circuit, or omega C. So what we're looking for is the frequency where the output hits negative 3 decibels. And we're looking at that specifically because what negative 3 decibels correlates to is exactly half of the power supplied by your input signal is being transferred to the output. It's based on what the fundamental definition of a decibel is, which I guess I should probably explain to you guys. So let's circle back around to that real quick. All right. So let's talk about the decibel. So if we have inherently our transfer function here is a ratio of output voltage to input voltage. If we want to express it in terms of decibels, then we have 20 log V out over V in. And let's say specifically the magnitude of the output voltage divided by the magnitude of the input voltage gives us H of omega with units decibels. Okay. Now, because of the nature of this operation, an alternative definition would be 10 log P out divided by P in is equal to H of omega measured in decibels. When the ratio of P out to P in is exactly 1/2, is negative 3 dBs. So our half power frequency will occur when omega forces, let's see, V out divided by V in to be 1 over the square root of 2. So whenever we have our magnitude response, which we found up here, whatever frequency causes that to be exactly equal to 1 over the square root of 2 will be our corner frequency for these first order low pass filters and first order high pass filters and all that kind of stuff. And we'll do a similar derivation for what our corner frequencies will be when we get our, when we start dealing with our second order terms. So as a quick aside here, let's figure out what our corner frequency is going to be based on our frequency response. Okay, so how am I going to make this relationship look like 1 over the square root of 2? Under what condition does that occur? What specific value of omega? I mean, so I have my numerator already taken care of. I have a 1 in the numerator for what I'm looking for, and I have a 1 in the numerator, so I'm good there. Then I have 1 plus this other quantity, and that everything underneath this radical sign needs to be equal to 2, right? Which to me implies that this guy right here, omega RC quantity squared, needs to be equal to 1. So what value of omega makes that happen? Well, if we know that omega, I don't like that color, it's too dark, looks too similar. Omega RC squared is equal to 1. We can take the square root of both sides, right? Which gives us omega RC is equal to 1. We don't need to worry about a negative frequency. So that means that omega is equal to 1 over RC. So that is our half power frequency for this particular filter. So let's verify that, okay? We chose a value of 1 kilo ohm, and we chose a value of 1 microfarad, I believe, for our filter. So our frequency, 1 over 1,000 times 1 times 10 to the minus 6. This says we should be at 1 kilohertz. Let's see if that's the case or if I've made a boneheaded mistake somewhere. So let's move this guy out of the way. 1 kilohertz certainly seems reasonable, except that it's looking like I'm getting minus 16 dB. I did say 1K and 1 micro, right? Well, let's just play around with things and look at what's going on. Distinct possibility I've made a simple mistake somewhere. If I click on this guy, I get some markers. And so I'm looking for when my magnitude is really close to 3, or -3 specifically. All right, so this is telling me that I should be looking for a frequency of 160.2895 hertz or thereabout. So why am I not getting that? Let's take a look back at this guy real quick, okay? We're not using an inductor, so that there shouldn't be any automatic series resistance added to any of our elements. I feel like I've just made some dumb mistake here probably in how I'm defining the corner frequency explicitly. Like, oh, I feel like a jackass. This is what happens when I don't bring the notes to class. So we need it to be 1 over square root of 2, which means we have linear frequency and angular frequency here. So there's a factor of 2 pi that I have neglected, right? So we need omega to be equal 1 over RC. And so that means F, our linear frequency, should be 1 over 2 pi RC, I believe, right? So let's try this. 1 divided by 2 pi, pardon? 159 hertz, is that what you got? And I'm saying it's 160 and some change there. So it seems, and we're at negative 3.04. So, okay, so I didn't screw it up. I just forgot that this guy is using things in hertz and we're developed everything in terms of omega. So our simulation predicts the exact point that we expect. Okay, good. So the mistake wasn't as bad as I thought it could have been. Wonderful. All right. So let's circle back around and work on a slightly different circuit. And we'll go through this one reasonably quickly because we only have like 20 minutes left of class. So before I had a resistor up here. Let's place the capacitor there, our resistor here, and see what this guy gives us. Plus V in plus V out. All right, so right off the bat, we should easily be able to tell what our transfer function is. So I'm going to say H of omega. I keep writing the magnitude signs when I don't need them yet. Is going to be R over R plus 1 over j omega c. If I multiply the numerator and denominator, I get j omega rc divided by 1 plus j omega rc. If I multiply this then by 1 minus j omega rc over 1 minus j omega rc, I'm going to get a denominator of 1 plus omega rc quantity squared. And let's see, I'm going to have omega rc quantity squared minus j omega rc, which I can split up as omega rc quantity squared over 1 plus omega rc squared plus negative j omega rc divided by 1 plus omega rc. All right, so I have my real part, I have my imaginary part, all that jazz is taken care of here. Just double check my math here because I went through that crazy quickly. So j omega RC times 1, I should have positive here. And then j omega RC times negative j omega RC is negative j squared, which is positive 1, omega RC times omega RC, so 1 omega RC squared. All right, so that seems legit. So our transfer function then we take the square root of the square of the real part, add to that the square of the imaginary part, so this is going to look like the square root of, so I'm going to have 1 plus omega RC squared as a common denominator, and then I'm going to have omega RC squared times 1 plus omega RC squared, like so. This guy cancels this guy, and we get omega RC divided by the square root of 1 plus omega RC squared. Just to test things here, when omega is equal to 0, the magnitude of h has to be equal to 0 because we have 0 in the numerator. When omega is equal to infinity, we have infinity divided by the square root of infinity squared. So infinity over infinity looks like 1 to me. So this is obviously then a high pass filter, right? Because all of our low frequency terms are attenuated, all of our high frequency terms are passed. Our phase angle theta of omega is going to be the arctangent of the imaginary part, which is omega RC, divided by the real part, which is omega RC squared. So this should be 1 over omega RC. What is our corner frequency going to be? Or cutoff frequency, or whatever we want to call it here. So again, we are looking for, we can prove it pretty trivially, but for our high pass filter, our minus 3 dB frequency is still going to happen when the ratio of our output voltage to our input voltage is 1 over the square root of 2. So if we have 1 over root 2 is equal to omega RC over the square root of 1 plus omega RC quantity squared, how do we manipulate this guy to figure out what's going on, right? Well, let's square both sides so that we'd have 1/2 is equal to omega RC squared over 1 plus omega RC squared. So we could have 1 plus omega RC squared is equal to twice omega RC squared. If we subtract omega RC squared from both sides, we get 1 is equal to omega RC squared, which means that omega is 1 over RC and F is 1 over 2 pi RC. So we have the exact same cutoff frequency for our high pass filter and our low pass filter. We got 15 minutes left. So before we move along to an inductor circuit, anybody have any questions about this one since we went through it so rapidly? Fairly straightforward, right? The process, once you understand what the process is, it's pretty simple. All right, so now let's throw some first order inductor circuits in the mix. So we'll start with R up here, J omega L here, in, out, our transfer function, what are we going to have this time? Is it still a voltage divider? Yeah. J omega L, right? Because we got an inductor in the mix now. So J omega L divided by 1 plus J omega L. We don't have any fractions or anything like that to clear, so that seems pretty good. If we want to break it down to a rectangular form, which is what we've been doing, we could put 1 minus J omega L here and 1 minus J omega L here. That is going to give us omega. Oh, no, hold on just a second. There shouldn't be an R, or there shouldn't be a 1, it should be an R. I apologize for that. I was used to writing the 1 from the capacitor, right? So we're going to have J omega L times negative J omega L is negative omega L squared, right? Yes. And then plus J omega RL divided by R squared plus omega L quantity squared, which gives us this guy. All right, so our magnitude square of the real part plus the square of the imaginary. Okay, so we're going to have a common factor of R squared plus omega L squared quantity squared. In our numerator, we're going to have omega L to the 4th power plus omega L squared R squared. So that's going to look like omega L squared times R squared plus omega L squared. This guy cancels one of those guys, and so we're left with omega L over R squared plus omega L squared. So there's our magnitude. When omega is equal to 0, our output is 0. When our omega is equal to infinity, our output is 1. So this is a high pass filter. Our phase angle, theta as a function of omega, is the inverse tangent of, let's see, our imaginary part, omega LR over omega L squared. R divided by omega L. Our corner frequency, exact same definition as before. It's going to occur when that ratio is 1 over the square root of 2. So that means that we would have 1/2 is equal to omega L squared over R squared plus omega L squared. Which means R squared plus omega L squared is equal to twice omega L squared. We subtract omega L from both sides. We get R squared is equal to omega squared L squared. Omega is equal to the square root of R over L, and F is equal to if I did that algebra correctly. I didn't. There shouldn't be a square root there. Right, because everything is squared. So omega squared is equal to R squared over L squared. So omega is equal to R over L. So there we go. That's our corner frequency. All right, so we only have 5 minutes left. So instead of going through the motions here, what do you think is going to happen when we transpose the resistor and inductor in this network? So we already had a high pass filter, so it'll be a low pass filter. It'll be a low pass filter. I think the only change here is in our transfer function. Oops. We should have a 1 in the numerator. You can mathematically prove that pretty easily. And then it's going to flip the angle, so we should have omega L over R, I believe. Our corner frequency is going to stay the exact same thing. I'll leave it as an exercise for you guys to verify those results, but it's fairly straightforward. It's nothing different than what we just did. It all just stems from the fact that at the very beginning, we're going to have R over R plus J omega L, and then go from there. All right, so I think that's enough out of me for today. So when we come back on Wednesday, you have a test. So Friday, then, we will cover second order filter circuits. We're not going to look at low pass and high pass filters with second order quantities because there's not enough time. But you can absolutely make them. I might show you how to do it, but we won't go through deriving everything. We'll only work on deriving stuff for a band pass and a band stop so that you'll know how those behave. And then I'll probably give you a little design problem where you'll set up a filter circuit with a specific bandwidth that would pick up our local radio station. And then that'll be good to go. All right, so exam is on Wednesday. All of the lecture video recordings and all that stuff have been uploaded over the weekend. I am in the process of getting your homeworks graded, and by that I mean I'm harassing my grader. I am personally in the process of grading your exams, expect those grades. If not tonight, then tomorrow morning at the absolute latest. So I'll have I'll have exam 1 finished up, like I said, by tomorrow. Working on getting several of your homeworks finished, and then all day Thursday will be spent grading the in-class portion of exam 2 so that you will have a very good idea of how you are doing in this class so that you can make an educated decision as to stay or drop on the drop date on Friday. Sound good? All right, see you guys later.